problem, let's assume that we have a function r, big capital R, a function of small r, and it looks like this. What we can do here is that we can determine what is the derivative of this function r with respect to the small r, and this is going to be a times L to the power r minus 1 plus b times, we know what derivative does, right? So we have r to the power n, the derivative is always m times r to the power m minus 1, right? So this is the derivative. So then let's take this power down here, so this is going to be times minus L minus 1, right? R to the power minus L minus 2, okay, that's the derivative. And then we can multiply by r squared. If you multiply by r squared, this is a L, r, L plus 1, let me make sure, is it true? Yes. Plus b times minus L minus 1 times r to the power minus L, right? Because minus L minus 2 plus 2, this is what we get. Now, at this stage, what we can recalculate again is that we can take the derivative of this expression again. So let's do d over dr of r squared dr over dr. So this means that we are taking the derivative of this function here with respect to r. This is going to be, again, the same principle. We have a times L plus 1 times r to the power L, okay, because we decrease the power by minus 1, and then plus b times, since we take the derivative, we see that whenever we take the derivative of this term, the power comes down, and then the power that will come down will be minus L times minus L minus 1, and then what is this? R to the power minus L minus 1, okay? And then if we see here carefully, we may notice that this term can be to the power minus L minus 1 br, and this term, these are equal to this initial function. These are equal to here actually. So okay, so you can see this term is here, this one is here, and this one was written only for reference. We know how to take derivatives, but it's good to write them on the corner when the terms can get a little confusing. So we know this here, and we know that this minus minus, you can multiply, you can factor out the minus, you can make this like this, okay? But then finally, this would be L times L plus 1 times RR. Okay? So this is something that we observe for this specific function. Now, in the previous example, here, we were analyzing how the potential, how the solution of the Laplacian equation can be in case the potential is a separable function of x, y, and z. Now, let's assume for a moment that we are in spherical coordinates. This is Cartesian, or spherical coordinate system. What are spherical coordinate systems? It's r, it's theta, and phi. Okay, so this will be the spherical coordinate system. You can read up here, and then we have to write down the Laplacian in spherical coordinate system. The Laplacian, let's write it here because it could be a little long. So Laplacian in spherical is 1 over r squared, d over dr, r squared, dv over r plus, now, sorry, this is capital R, because, no, we might get confused. Let's keep it little r. Maybe it's better if we do it like this. 1 over r squared. This is r squared again. dv over dr plus 1 over r squared sine theta. d over d theta. Sine theta dv over theta plus 1 over r squared sine squared theta. You can read that part. The second derivative of v with respect to the third component. Okay, so this is the derivative which corresponds to r. This is the derivative with respect to theta. And now here we have the second derivative of v with respect to phi squared. This will all be equal to 0. And the last derivative is not like this, but it's a partial derivative. And so this is the Laplacian equation in spherical coordinate system. Let me write here. Laplacian. That's good. Now, in this problem, we are going to assume azimuthal symmetry. Azimuthal symmetry, this means that we can imagine for a moment that you have an antenna. So, you have an antenna which might be transmitting the signal for your cell phone. And the antenna is sitting somewhere, and often there is no difference if you are sitting in the front of the antenna or on the back side, or if you are on the right side versus to the left side. This means that there is a symmetry, azimuthal symmetry, or which means that the derivative of the values that are transmitted by this antenna, they will be independent of phi. So here, we may assume that the derivative of the potential with respect to the angle phi, this is 0. Okay. So we better assume this because most of the cases, most of the different configurations, they do observe the symmetry. And let's consider this one like this for a moment. This means that the third whole term, it is cancelled out. Now, we may assume in this part that the potential as a function of r and theta, this is equal to r and theta theta. Okay. So let's assume that this is a separable function, the same way we did when we solved this problem. Now, if we, and also let's check again. Now, since this whole function is equal to 0, I believe, now let's take this away. It might take too much time to write it all from scratch, but imagine for a moment this is 0. If this is 0, we can very easily multiply here with r squared, here with r squared, and here with r squared, okay? So we multiply everything by r squared, then this will still be 0. Sorry, this is 0. And here we cancel out these, and the system gets a little simpler. And then, so we can see it actually, it's just the derivative, yeah. So we can write it here, d over dr, r squared. Now, assuming that this is a separable function, we can obtain, this is 1 over r, wait a second. D over dr, r squared, dr over dr, plus 1 over theta times 1 over sine theta, d over d theta, sine theta, d theta over d little theta. This is all equal to 0. Okay, so this was the Laplacian spherical coordinate system. Once it is separable, we get this. Now, we said that once it's separable, we get this. But in this case, we're just going to assume that this dependency of capital R on R is going to look like this. Okay. So if this function behaves like this, where L is just a number, then we can easily see that actually we solved this one, right? Now, what we have found here is this part. So, this element here, it's right here, okay? So, we have found it, and this one, it is equal to L times L plus 1, and this whole section, all the rest, this is minus L times L plus 1. And this is equal to 0. So, if you remember, when we did the solution for the Cartesian coordinate system, we found that we had C1 plus C2 plus C3 was equal to 0. Now here we observe that constante C ni është tani veç është mëson 2 plus 1, dhe constante C2 është minus 2 që është mëson 2 plus 1. So, this is what we're going to write these. And by the way, if we reorganize this one, not reorganize, we can say that d over dr times r squared, dr over dr minus L plus 1 times r, this is 0. So this is the differential equation. Now we know this is equal to, because this whole term, it was L times L plus 1, minus the same term, this will for sure be equal to 0. So this is the solution. Okay, we got it. So this is the solution. Now, if this is the solution for R, and in fact this is a wonderful type of solution because the terms that we observe here, they are polynomials. We know that the polynomial, it looks like this. It has x to the power 0 plus 3 x to the power 1 plus 4 x to the power 2. So we are dealing with a polynomial solution, and polynomials are the simplest functions to work with because it is very easy to integrate x squared, right? It is x cubed over 3. It is very easy to take the derivative of x squared because it's 2 times x. Those are the simplest things to work with. So once you see any expression like this, even though maybe we haven't seen this before, you should feel comfortable once you know that it's simply going to look like this. So it looks like R, we found it. The question is, what could be this other function, theta, capital theta, as a function of the coordinate theta? This is going to be a polynomial, which we call it Legendre polynomial. Now, Legendre polynomial, again, when I was a student also, once I see this keyword polynomial, I said, okay, that's easy, okay, that's good. So I should feel good about it. So this was a polynomial, super easy. This is also a polynomial, that's good. And we should be okay. So this is how the solution of this problem in the spherical coordinate system is going to be. Now, we're not going to solve any example for the moment, but since I gave this exercise at the end of the previous session, we just went over with this, and I hope this is good. But one other thing that I may have to add is that these Legendre polynomials, they have some wonderful properties, which will make your life much easier. And because these functions, we can they can be generated, or we can draw a recursive relationship for all of these. Now these polynomials, this is PL, this means polynomials of degree L. For example, P, this is a function which has 3x to the power 3 minus 2x squared minus x plus 5. Okay? So we see that a polynomial of degree 3, it includes a term, or the largest term, it is x to the power 3. It could have x to the power 2, it's good, it's possible. X to the power 1 and x to the power 0. So we can write this 1 times x to the power 0. This is x to the power 1. Now, these Legendre polynomials, now we are going to write the Legendre now this was just a second. This is any polynomial, let's call this L. Because with PL, we are calling these passage functions, and this is not degenerate, so that we don't get confused. But now let's assume we have a polynomial of 0th order and degenerate. This is equal to 1. A polynomial of degenerate polynomial of the first order. This is equal to x to the power 1. Okay. A polynomial of second order in x. This is equal to 1 over 2, 3x squared minus 1. So, these polynomials, they do have a recursive relationship. I have not memorized this one. It is a little difficult how to obtain this, but let me check if I can find it in my notes. Otherwise, I will not. Wait a second. Let me see, because it is interesting if you derive the subsequent degenerate polynomials once you are given a couple. When you say once you're given, okay, I found it. So our principle in the class is the following: if you can do it in less than 2 minutes, do it in the class, okay? Or do it in the board. Very good. 1 plus 1. The relationship here is 1 plus 1 times Pn plus 1 x. This is equal to 2n plus 1. 2n plus 1 times x. Pnx minus n, Pn minus 1x, okay? This is the recursive relationship. Let's assume that from the degenerate polynomials, we just know these two, okay? The 0th order is 1, the first order is x. Then, let's try to substitute. Let's set here n equal to 1. Someone from you in the class, you can read, or let's do this together. Kush do të krij dorën ta zgjidhim këtë? Apo zgjedhun? Andrea? Ose Brandon? Brandon?
Yes.
Can you help me here? Brandon, let's substitute.
I have a problem with reading the equation. Can you lower the board? Mund ta ulësh pak tabelën për shkak se nuk e lexoj dot ushtrimin.
Reflecton, huh? Oh, let me see this one. This is equal to 2. What part are we missing? So I'll try this. Reflecton drita, që do thotë, let's look at this. A duket mirë?
Tani më mirë.
Okay, so let's substitute n equal to 1 here. What should I write? N plus 1.
2.
Oh, 2.
2 për 2.
Oh.
X barabart me 3. X për 1x.
Oh.
Minus nishin nuk do e shkrim për 2x. Për 2x. Ja, për 0.
Për 0x. Shumë mirë. Okay, now in here we know what is P1x. P1x, we know this. Okay, it is x. And we know also what is P0x. This is 1. So then from here we just need to write, let's do it like this. We see that P2x, which is the degenerate polynomial of the second order, we have to divide both sides by 2. Okay, would you agree, Brendan? So this is 1 over 2 times 3 times x times what?
The x in power 1.
Yes.
P1x.
X minus
1.
Minus 1. That's good. Minus 1. So this is equal to 1 over 2, 3x squared minus 1. So this is the polynomial of second order Legendre type, okay? And we confirm is this one that we wrote before y, right? So again, help me again. Let's substitute n equal to 2. If we substitute n equal to 2, can you read it? In here?
Again, me?
Yes, you.
3.
Yes.
P3x.
P3. Yes.
5x.
Yes.
P2x.
Yes.
Minus 2 P1x.
Okay. Now, P2x, this function, we know what it is, we found it here. P1x, we know what it is, it's just x. So then this means that we have here P3 of x, this is equal to 5x times 1 over 2 times 3x squared minus 1 minus 2 times P1x, it is x, right? This is minus 2x. And then this will be equal to, let me see how much you can see. Yes, you see some more space on the board. So this is 5 over 2. 5 over 2 times 3, this is 15. Let's do it like this. 15, because this 3 goes out. 15 over 2 x cubed. 15 over 2 x cubed. What is this? Minus 5 over 2x. Minus 5 over 2x minus 2x. Okay, so it looks like the P3 of x, the polynomial, Legendre polynomial of order 3, it is equal to 1 over 3 times. Let's do a couple of manipulations. This is 15 over 2 x cubed. What is this now? This is minus. Who can do this one? This is minus 5 over 2 plus 4 over 2x, which makes it minus 9 over 2x, right? Minus 9 over 2x. And this is equal to, let's insert the 1 over 3 here. This is 5 over 2 x cubed minus 3 over 2x. We can also factor out 1 over 2. So let's factor out 1 over 2, and then this is going to be equal to 1 over 2, 5 x cubed minus 3x. Okay, so this is how we can generate the third order Legendre polynomial, the same way we can generate the fourth and the fifth and so on. And so these are polynomials, okay, the first, so imagine now you have a solution, and now you need to find the derivative of the third order polynomial. It's easy, okay? I mean, the derivative of x cubed is 3x squared, that's it. Now, right out of this, we have to add a couple of more information. The value of x here, it is like this, minus 1, 1. Okay, so these polynomials, they preserve their properties once they are defined from minus 1 to 1. Now, what are some functions that can be from minus 1 to 1? This can be sine and cosine, okay? This could, and let me also add something which is essential, that the third order polynomial, this is an odd function, okay? This is an odd function. The second order polynomial, which is here, it is obvious, so P2x, this is an even function. The first order polynomial here, this is odd, a function tech. The first order, zeroth order polynomial, this is even. So what we can observe, if we keep calculating the subsequent polynomials, we will notice that they will become once even, once odd, once even and once odd. And okay, this is something interesting. And another aspect, so the solutions for the spherical coordinate system. In these polynomials, we will have that x is equal to cosine theta. Okay, so which means that this polynomial effect is P3 in cosine x. This is going to be equal to 1 over 2, 5 cosine to the power 3 minus 3 cosine. That's it. Okay, so this is how they are going to look like. Yes, now. These are the Legendre polynomials. I want you to have a look at these. I mean, the tools or the mathematical apparatus is not that difficult, but we went over these specific problems by doing the relatively challenging solution. Now, we have let me wait for a second. Okay. Let's solve one example, but now let's switch for a moment to the Cartesian coordinate system. This was the spherical, but let's see. Okay. First, let's pose the problem. Let's assume that we are given a couple of metal plates. So this is Y, this is X, and we have an extension here along the Z. And we have a plate which extends for large values of X that looks like this. And then we have another plate which extends like this. Now, the bottom plate, let's draw it here, and this is the top plate. So we have two conductive plates that they are at a distance A. So the first one, it is at point 0. The second one, it's at the distance A. And what we do to these is this. It absorbs. So we ground these two together, and so they are far away from each other. I mean, it's far away. They are by distance of A. And now we are dealing with boundary conditions. Let's give the boundary conditions. The first condition is that the potential at y equal to 0 is 0. The potential at y equal to A, it's 0. So these are two initial conditions. Then we have the potential, it's equal to V0y at x equal to 0. And then we also have that the potential converges to 0, or let's do it like this. When x diverges to infinity, this is equal to 0. Now, we could draw this one also like this, converges to 0, but we understand what we're talking about. So, diverging here converges here. So we have four different initial conditions, which means that the bottom plate is grounded, potential is 0, the top plate is grounded, potential is 0. This plate, which is in red, has the potential is non-zero, it is some function of y, okay? So this is all we are given for this specific problem. Now, what are we going to obtain? We immediately have to write down the Laplacian operator. Laplacian is this, okay? Then we get this, the second derivative of x, this is capital X, with respect to x squared plus the second derivative of y with respect to y squared plus the second derivative of the capital Z with respect to parameter Z, this is 0. Now, one thing that we can observe here is that we may have to use the symmetry of the problem, and notice that if we move along this line from here to here to here, and also from here to here to here, which parameter are we changing? Ce po ndryshojmë ne? Kur shkojmë nga kjo pikë këtu te kjo pikë këtu. Ose nëse jemi këtu, nëse shkojmë gjatë vizës, çfarë po ndryshojmë? Po ndryshojmë z-n apo jo? If we change the z parameter, we observe no change in the potential. Okay? So, is it clear? Është e qartë. So this means that this Laplacian operator, this can be simplified a little further. Okay, so this differential equation, it simplifies into this expression. Then we expect this to be a constant C1, and this is another constant C2. Okay, and then we can say that C1 plus C2 is equal to 0. Now, so far, we have not done much new information. Okay, so we know what the Laplacian equation is going to look like. It will end up something like this. But the big question is the following. So Z is not part of the problem. So Z, the potential, it is independent of the parameter Z. Because as we said, if we move across this line, we observe no difference. Then what we can say is the following. What would you expect for the potential to change along the value of y? So if you are going from this point, from the bottom plate to the top plate, what type of solution would you expect here? Oscillatory or exponential? It's 50% chance, either one or the other. Which one would you choose? Brandon, so we're asking this one. If we move from here to here, the dependency of Vy, so we're asking this, Vy, is it going to be an exponential which looks like e to the power minus ky y, or is it going to look like cosine ky? Which one would you choose? The first or the second? Brandon, did you know
First.
So you are choosing a dependence of exponential moving between these 2 points. Okay, but then let's try the following. Let's substitute. Let's apply y is equal to 0. If we substitute y is equal to 0, what do we find? Potential at y equal to 0 is equal to what?
One.
Exactly, that's 1. So it's 1 volt. That means like a battery, a AAA battery that you use for a remote controller in your home. You have charged it from ground to 1 volt. Okay, that's 1. That's okay. What about the top layer? Okay, you are saying that the potential V at y equal to A. Sorry, this is A because this is distância A, not the placa. What do you get here? You get e to the power minus ky times A, right? But don't forget that the bottom plate, this was 0, right? And this was also 0. So, does this look like a good choice? Brendan?
Not anymore. Not anymore.
Okay, if it doesn't look like a possible choice, then we are left with the second option, which is the second option being that this potential, as a function of y, it is going to look like cosine ky. Well, let's multiply by a constant. This is equal to c1 cosine ky plus c2 sine ky again. Okay. Then, if we look at this expression, okay, so it looks like this is the potential. The next question, what could be the dependency along the x-axis? So let's ask this, what is Vx? Could it be e to the power kx or cosine kx? Which one would you choose? It will be either the first or the second. I mean, it's not a Russian roulette. It's something simpler. You can toss a coin. Why don't you do that? Good as you, Brandon, which one would you choose for the dependency on x? Or the second?
Nëse do shkonim me logjikën e shembullit me y-in, do zgjidhnim prap cosine kx.
Bukur. That's okay. Let's choose this. Okay. Why? Why would you choose that?
Because the plate if we take x equal to 0 and x equal to another number, the potential should still be 0 because the whole plate is grounded.
Okay. But let's choose this one. And then let's try to implement or to use this boundary condition as a function of x, which means that the potential at x equal to 10 to the power 6, okay, it's a large number, it's like infinity. 10 to the power 6 meters, it is infinite, depending on what the dimensions are here. Or you can either write it like this, Vx equal to infinity, okay. What is this? Is this 0? This is cosine. Cosine never converges to 0. It oscillates. It goes from -1 to +1. Okay? So cosine, it is not a very good choice. The potential as a function of x is going to be something like c3 e to the power kxx plus another constant c4 e to the power minus kxx. Okay? So these constants, they might be, in fact, they are not different because c1 is equal to negative c2. So let's use only one k here. Okay. So, Brandon, I believe that the potential as a function of x, it would rather be an expression that looks like this. Would you agree with this now?
Yes.
Okay. So now, so far, we didn't do too much difficult mathematics. We just use our intuition. This is the solution, okay? So this is how easy this is, or this is how difficult this is. So we know that it should look like this, then we got it. So whenever we have a region which is bounded, we may choose the option of having an oscillatory dependence, which in this case, it can be something like this, okay? Or it can have a higher frequency like this. So this would be the expression for the potential, or a much higher frequency like this. All of these are possible, but they all look like sine and cosine. Now, so it looks like the potential itself, the V, as a function of x and y, it's equal to the multiplication of c1 cosine ky plus c2 sine ky multiplied by c3 e to the power kx plus c4 e to the power minus kx. Okay, so this is our potential. We found the solution. only that we are given some initial conditions. Okay, so let's try to implement those. As a function of y, so can we try to implement? So let's do this boundary condition. Let's work on this one. Okay, v potential when y is equal to 0. Okay. So I want someone else other than Brandon to help me here. Kush Grendor. O să zi domnul poate să din zero na Victor. Acțiune.
Profesor. Profesor, este în advent mugen vostero pico, profesor.
Păi atunci lor. Acțiune din nou. Dozăruțuim zero. Take your proiectul. Ce de V, when y is equal to 0, is equal to what? This is C1. Go ahead, cosine.
0.
Cosine 0. K times 0, so okay, let's go. Let's do this 0. Plus C2 times what?
Sine 0.
Sine 0. Okay. So we just substituted. What is this equal to? So, such potential equals to 0.
0.
It's 0, that's true. Because this is the bottom plate down here. But now, let's have a look. Cosine 0, what is this cosine 0? 1, right? Would you agree?
Yes.
So what do we get then? We get here C1 plus what?
Plus 1.
No,
I mean, 0.
Plus 0. It's equal to what?
C1.
C1. And then the whole thing is equal to what?
0.
0, right? So it looks like C1 is equal to 0. This term is gone. Then, so we kind of simplified a little bit the problem. And then let's implement the second boundary condition. Let's do this one. So here we have the potential when y is equal to a, because now we are at the potential at the top plate. This is equal to, so C1 is gone, right? So what was, so let's write this again. So since C1 was 0, it looks like this is going to be C2 sine ky. Okay? So we simplify this, and now, Artyoda, now substitute y equal to a. What should we write here?
C2 sinus a.
What?
Ka.
Ka, okay. What is this equal to? Saç potenciali de plaka e sigurme. Është të gëzuar kjo. Would you agree that this is 0? So the top plate, this is equal to 0, but this is sine. When is sine equal to 0? Let's have a look at the sine function, how it looks like. Sinus, sine, it is 0 at angle 0. It's also 0 when the angle is 180. Or let's try this one, pi. It's also 0 when the angle is 360. Would you agree, Arturo?
Yes.
It's also 0 when it is 3 times 180, or let's write it like 3 pi, okay? 1 pi is 180. Again, it is 0 when the angle is 4 pi, and again. This is 5 pi. So all of these zeros, they are equal to sine and pi, okay? We put no restriction. So sine, it gets 0 in these values. at this stage, it looks like the k times a, this is equal to n pi. But let's not forget, what was n? N, it was equal to 1, 2, 3, 4, 5. Okay, there are these numbers. So it looks like we know n, right? It's just a number. We know pi, it is 3.14 radian. We know a, it's a given. So this looks like the value of k is equal to
n pi over a.
pi over, that's true, okay? So this is the value of k. So it looks like we can pick up too much information in this whole expression. Now, let's try to implement this boundary condition here for Vx in this expression. So we said in the previous session that when the solutions look like exponential terms, we keep some terms and we don't keep some others. Which one would you choose here to keep?
C3.
You want to keep C3, right?
Yes.
So then it looks like this potential is going to be equal to C3 e to the power kx. Are you okay with it? Then let's try to implement this term. Let's draw the graph. Search graficul n funcție x. Ce formă are? E de acord?
Da.
Eu știu n funcție kx, spre exemplu. Poi n funcție minus kx.
Ja, not yet.
Okay, so this is e to the power minus kx. Now, out of these two possible functions, which one converges to 0 when x is positive? Which one converges to 0? This one or this one?
The second one.
You mean the green? So, yes, this one converges to 0. This means that this is not correct. Okay, so what we should get, we should consider that C3 is equal to 0. Okay, and then here we should get C4 times e to the power minus kx. Okay, then this means that C3 is also 0. And so please don't make mistakes here. So we are progressing along the positive axis, so we should keep the second term. Now let's put here on the board everything that we found so far. The potential V as a function of x and y is equal to what? Let's read this from here. C1 was 0, so then this is going to be C2 times sine of ky. What is k? K, it is n pi over a y. Okay, multiplied by C4. C cadra is constant. Nu goes this percent like C4. It's not an explosive. It's just a constant. So then we have here e exponential minus k. It's n pi over a, n pi over a x. Okay. So this is the solution of our problem. Is it clear? Do you have any question? Wait a second. Okay. Oh, wait, what happened? You cannot see the other side. Oh. Apologies. Okay, now I see it slightly better.